Hello, everyone. Welcome to section 3.5. This section is on complex zeros and the fundamental theorem of algebra. This section, we're going to start off with a lot of theorems. We're going to start off with a lot of different little rules. We're going to do examples of them. But then we're going to see why we care about these theorems and how they're useful and what we're going to do with them. But first, let's go ahead and talk about these theorems. So the first one, the first rule we're going to talk about is called the fundamental theorem of algebra. Okay. And the fundamental theorem of algebra says that for every polynomial, so let's call it P of X, and let's say it's of the form A sub n, where that's the leading coefficient times X sub n, so n is the degree of this polynomial, plus then the next term is A sub n minus 1 to X n minus 1, all the way down A naught X linear term plus, or sorry, that should be an A1, and then A naught, that's the constant term. And then this polynomial is with complex or real coefficients. So all the A1, the A naught, the A1, all the way through A sub n minus 1, the AN, all those coefficients are real or complex numbers. This polynomial has at least one complex zero. So despite its name, the fundamental theorem of algebra, we're not going to be using this theorem a lot. I'm showing it to you so you know what it looks like, and you know what it is. And I'm also showing it to you because the rest of the rules, it turns out, are kind of built upon this fact. But you don't need to know how they come from each other, et cetera, et cetera. I just wanted to show this to you so you've seen it and you know what it is, but we won't be using this at all for anything. The next couple ones, we will be using them though. So those will be a little more important for what we're going to be doing. So the next one is called the complete factorization theorem. Okay, and what this says is if we have some polynomials, so if P of X is a polynomial, now let's say it's of degree n. So here, since the polynomial degree n, n's got to be bigger than or equal to 1, then there exists complex numbers let's call them A, C1, C2, all the way up to C sub n, where we're going to say A is not 0. So you can find them, these numbers A, C1, C2, all the way to Cn, such that we can write P of X as equal to A times X minus C1, X minus C2, all the way down to X minus C sub n. So C1, C2 through C sub n here, these are supposed to be the roots, the zeros of our polynomial P of X. And so what this theorem is saying is that we can take any polynomial and we can write it as a bunch of linear factors. We can completely factorize it, right? So let's look at an example to really kind of see what this is saying. Let's say, for example, we had a polynomial like 2x to the third minus 6x squared plus 2x minus 6. So it turns out you do some work, do some algebra, whatever, blah, blah, blah. You can eventually factor this to be 2 times x minus 3, x plus I, x minus I. So here, if we look at what our theorem is saying, for this polynomial, A is 2, and C1 is going to be 3, C2 is negative I, and C3 is positive I. And so you'll notice that the degree of this polynomial was 3, and there are 3 roots. And that's actually a key idea we're going to see in a rule in a little bit. But what this theorem is saying is that we can take any polynomial, in this case we've got this one here, and we can completely factorize it, so that we will always be able to do this. It's just a question of figuring out what the factorization actually is. Okay, let's look at our next rule. Our next rule is called the zeros theorem. So this says that every polynomial of degree n has exactly n zeros. So this is exactly what I was saying just a minute ago. You have a polynomial of degree like 4, you're going to get 4 zeros. The polynomial of degree 32, you're going to get 32 zeros. So, and then this next thing I'll explain in just a sec. As long as the zero of multiplicity k is counted k times. Okay, that little parenthetical, it looks a little weird, a little funky. What does that mean? K times k multiplicity? I might remember from a couple sections ago what that means, but let me illustrate with an example just in case you needed a refresher. So what this theorem is saying is if we have some polynomial like, let's say, x to the 4th minus 6x cubed plus 11x squared plus 12x plus 18. So let's say we've got this random polynomial. You'll notice it has degree 4. So we're going to expect 4 different roots. If we were to take this polynomial and fully factor it into linear terms, we would see that it is x minus 3 times x minus 3 times x plus I root 2 times x minus I root 2. So here, the roots are 3 with multiplicity 2, right? Because there are 2 3s right here and here. And then we also have negative I root 2. So here, let me color coordinate these. So the 3 is green, the negative I root 2 is right here. And then lastly, we have a positive I root 2. Like that. Okay, so this polynomial has degree 4 and has 4 zeros. And it's 4 because we're counting 3 twice because it is multiplicity 2. Okay, so this is an important idea that, like, if you have a degree n polynomial, you can find n zeros. This is something that will also pop up as like an underlying idea of what we'll be doing. Okay, we have one more rule to look at. Let's just go ahead and do it. So this last rule that we're going to be talking about is called the conjugate zeros theorem. This one, I think, is probably the easiest to kind of understand what it's saying. So if a polynomial, let's just call it p of x, has real coefficients, so all of ours do, and any polynomial we'll be talking about so far and in this class is going to have real coefficients. All ours do. And if the complex number let's call this complex number a plus b times I. Let's say that is a 0 of our polynomial, so of p of x, then so is a minus bi, and vice versa. So if you're factoring a polynomial and you find that like 1 minus 2 times I is a root, then we also know that 1 plus 2I is going to be a root. So for example, if we look at from the above example, we had the polynomial x to the fourth minus 6x cubed plus 11x squared plus 12x plus 18. This thing had 2 complex roots. And I'm going to write them with the 0 in front just to make it really clear what's going on. The complex roots were 0 plus square root 2 times I and 0 minus square root 2 times I, right? Those, we go back and look up here, those are the ones that I've underlined in blue and red, right? So you notice we have a plus here, the minus here. So complex roots always come in pairs. Complex roots, they don't want to go anywhere without their buddies. You see one of them, you're going to have to see the other. That will always happen as long as your coefficients are real, which ours are. Okay, so why do we care about all these rules? Why are we doing this? The reason is because we want to be able to take a polynomial and we want to be able to completely factor it. We want to see what all its roots are. We want to see what it looks like with linear terms. Because when we do that to a polynomial, we get a lot of information about it. We can graph it, we can do all sorts of things. So this is the skill that this section is like really culminating in, is how can we completely factor polynomial. So I'm going to do 2 examples. I'm going to do an easier one first, and then I'm going to do a slightly harder one. So let's go ahead and do the easy example of how to completely factor a polynomial first. So let's completely factor. Let's do x cubed plus 2x squared. I'm not running out of room. Move it down. X cubed plus 2x squared plus 4x plus 8. Okay, so this is a cubic. And we want to go ahead and completely factor it. So we want to write it in linear terms. I'm going to go ahead, and because it's a cubic, I'm going to go and try factor by grouping first. So let's do first. Let's try factoring by grouping, which you might remember from previous sections. So looking at x cubed plus 2x squared plus 4x plus 8. Okay, I think what I'm going to do for this one is I'm going to group it like this. Okay, so I'm going to look at those terms, and I'm going to see that on this, in this kind of group right here, I have a common factor of like an x squared. I can pull an x squared out of both of those terms. Let's go ahead and do that. So we've got an x squared on the outside, and when I do that, I'm left with an x plus 2. Okay, plus, and then I'm looking at this one right here. I'm looking, what common factor can I pull out? Well, I see the first one is a 4 and the other one's an 8, so I think I can pull out a common factor of 4. Let's go ahead and do that, and when I do that, I think I'm left with an x plus 2. Okay, cool. So now we see that we've got an x plus 2 in both of these terms. What we can do is we can pull it out. And so we're left with x squared plus 4 all times, write some equal signs here, all times x plus 2. Okay, cool. We have our first linear term. So let me write that down. Now we have a quadratic, which is the first one. That's the x squared plus 4, and a linear term. That's the x plus 2. Okay. So the linear term is good. We've got that in the form we want. But now we still need to factor the quadratic. So we still need to factor the quadratic. Okay, so in order to factor the quadratic, x squared plus 4, I'm going to go ahead and use the quadratic formula. So here, just a little note for ourselves, a is equal to 1. That's the coefficient in front of here. There's nothing there. It's just secretly a 1. B is 0 because there's no linear term, and C is 4. So when I go ahead and use the quadratic formula to find the roots, and finding the roots will help us find the linear factors, I think that's going to be negative b, which is 0, plus or minus square root b squared, so that's 0 squared, minus 4ac, so it's 4 times 1 times c is 4, all over 2 times a, so that's 2 times 1. Okay, let's do some simplifying here. Minus 0, that just goes away, so we got plus or minus, and then 0 squared goes away as well. So we got minus 4 times 1 times 4. I think that's minus 16, all over 2. 2 times 1 is just 2. And now I'm going to go ahead and break up that minus 16. I'm going to write it as 16 times negative 1 over 2. And now I'm going to use our exponent slash radical rules and break up that square root over the multiplication. I can do that. Can't do it over addition, only do it over multiplication. So I'm going to write this as 16 times square root negative 1. That all over 2. Okay, plus or minus. And then square root of 16, that's going to be 4. And then square root of 1, I'm going to write that as I over 2. And then canceling the common factors of the 4 and the 2, we get plus or minus 2 times I. Okay, so what we just did is we found that the roots of that quadratic, x squared plus 4, we found that the roots of that quadratic are exactly 2i and minus 2i. So we can use the factor theorem. Which, if you remember, said c is a root only if x minus c is, you're not doing good with the spacing thing today. X minus c is a factor. So what we can do is we had x cubed plus, not a very good 3, cubed plus 2x squared plus 4x plus 8. And we factored it originally, and we got that it was x squared plus 4 times x plus 2. And then we factored the x squared plus 4. We found that its roots were plus or minus 2i. So we can write that as x minus 2i. That's the plus 2i root. And then x plus 2i. That's the minus 2i root. And then that is still times x plus 2. And that is a complete factorization of that polynomial. So this is what I mean by linear terms. Everything's like an x minus something or an x plus something, and they're all multiplying by each other. There could be a number out here, maybe like a 3 or 9. There wasn't in this case. That's okay. But yeah, that is a complete factorization. All right, let's look at maybe a slightly more complicated example. Let's completely factor. It'd help if I could spell. Let's do x to the 4th minus 2x cubed plus 3x squared minus 6x. Okay. So first, I'm looking at this, and I think what we can do, I think we can go ahead and pull out a common factor from each term. So if we notice each term has an x term, like we've got an x to the 4th, that definitely has an x. So there's x cubed and x squared, and then there's a minus 6x that has an x also. So all the terms have an x, so what I'm going to do is I'm going to pull out that x to begin with. So I'm going to go ahead and write this as x times, and then when we pull that out, it's going to be again x cubed minus 2x squared plus 3x minus 6. Okay. Now I could use factor by grouping on this thing right here, because we still need to factor this. But I'm going to show you a different way that will be more general and more useful for other higher degree polynomials. We're going to use that rational roots theorem to try to factor this. Okay. So let's look at all the possible roots. The possible rational roots. Let's see, our leading coefficient is, so remember, we're just looking at this thing right here. Our leading coefficient is 1, our constant coefficient, -6. 1 just has factors 1, 6 has 6, 3, 2, 1. Okay, so now if we write out all the possible rational roots, we have constant coefficient over leading coefficient. So we have plus or minus 6 over 1, plus or minus 3 over 1, plus or minus 2 over 1, and plus or minus 1 over 1. If we simplified these, this would be plus or minus 6, plus or minus 3, plus or minus 2, plus or minus 1. Okay, so the next step is we need to go ahead and check these, see if they're roots. I'm going to go ahead, let's go ahead and check if 2 is a root first. So remember, to check if 2 is a root, we want to take our polynomial, which in this case was x cubed minus 2x squared plus 3x minus 6. And we're going to divide it by x minus 2. Remember, there's a sign flip. And let's go ahead and do this division. And of course, you could do this as synthetic if you so wished. I'm going to go ahead and use polynomial long division. So we want to ask, what do we need to multiply the thing in the blue circle by to get the thing in the yellow square? I think the answer is going to be an x squared. So then we take x squared and multiply it by our divisor. So we get an x cubed minus 2x squared. Subtract that away. If we get 0 plus minus 2x squared plus 2x squared, that's another 0. Okay. And we'll drop down both these terms. I'm going to want 2 terms there. Okay, and now we're looking at this thing right here. Now we ask, what do we need to multiply x by to get 3x? And I'm pretty sure the answer is going to be 3. We get x squared plus 3 at the top there, and then we take 3, multiply it by our divisor. We get a 3x minus 6, subtract it away, and oh, we get a 0. So we have a 0 remainder. If you remember from last time, that means 2 is a root. So here's the thing that we can do now that we know 2 is a root and we've done this division this way, is that we know how to write this polynomial out. So if we take that polynomial that we divided, this x cubed minus 2x squared plus 3x minus 6, what we can do is we can write it as x minus 2 times something. So this came from the factor theorem, saying that because we know 2 is a root, we know x minus 2 is going to be a factor, and we can actually write this x minus 2 times x squared plus 3. That x squared plus 3 came from here. Okay, so you take your factor, your divisor, and you multiply it by your quotient. As long as there's a 0 remainder, this is true. Okay, so now we can go back and we know that our original polynomial is x to the 4th minus 2x cubed plus 3x squared minus 6x. We know that's equal to x times x minus 2, x squared plus 3. Okay. We still have to factor that quadratic. And by that quadratic, I mean this bad boy right here. I'm going to go ahead and just use the quadratic formula again. So here, a is 1, just like last time. B is also, just like last time, it is 0. And then c is 3. So if we try to find the roots of that quadratic using the quadratic formula, we get x equals negative b, which is 0, plus or minus square root b squared 0, minus 4 times a, which is 1, times c, which is 3, all over 2 times a, which is 1. Now we simplify. So that minus 0 goes away because it's 0. Nobody cares about it. And then we get a 0 squared also goes away. And we get a minus 4 times 1 times 3, minus 12. And that's going to be over 2. 2 times 1 is just 2. So we'll write it as that. Okay. I'm going to break up that negative 12. I'm going to write it as 12 times negative 1 over 2. Actually, sorry, I changed my mind. I'm going to break it up slightly differently. I'm going to write it as, I guess I shouldn't have written it as 12, but that's okay. 4 times 3 times negative 1, just kind of make it clear what I'm doing here. Then plus or minus square root of 4, square root of 3, square root of negative 1. And I get to break it up because we're doing multiplication, not addition. So that's still legal. And then plus or minus square root of 4 is 2. And then square root of 3. And then on the right, square root of negative 1 is I over 2. The 2's cancel, and we get plus or minus the square root of 3 times I. Okay, so now we know that the quadratic we started with, which was x squared plus 3, we use our factor theorem. We know that this is going to be x minus root 3i, x plus root 3i. Okay, so now if we pull all of this together, the thing we started with, x to the 4th minus 2x cubed plus 3x squared minus 6x. We can write that as x, that came from our first move, times x minus 2. That came from using the rational roots theorem and dividing. And then using what we just found, we can write that quadratic like this. Cool. All right. And that is a complete factorization of that polynomial. All right, so this process of completely factorizing things is long and arduous. So let's write out the steps, the kind of algorithm that we're using here. So the first step here is factor out any common factors from all your terms. Then two, second step is to find a root using any of the tools that we've developed so far. So something like the rational roots theorem. And you can also use any factoring techniques like factor by grouping, quadratic formula, although I'll list that separately in a second. You can use factoring techniques. And you can also use the quadratic formula if what you have is a quadratic. So you find a root using whatever, by hook or by crook. And then three is use the factor theorem. To turn that root into linear factors, or to turn roots into linear factors. And then lastly, step 4 is repeat. as necessary. So those are the steps to completely factor a polynomial. It's long and arduous, but it's important enough that I am going to expect you to know this, and I will expect you to do this. So I recommend you practice. There's a problem or two on the homework that asks you to do this. But let me know if you get stuck. It can definitely be confusing, especially when you're first starting out. Like, oh gosh, what do I do? This thing looks massive and scary. I don't even know where to begin. That's okay. That's totally normal. Let's work through it together. But yeah, good luck on the homework, and I hope to see you in office hours.